Hi, I'm Marie, graduate student in UCSC. I will present to you the latest results from the Quasars Probing Quasar survey. QBQ is designed to examine gas-related processes to learn about massive galaxy formation and quasar feedback. Redshift 2 to 3 is interesting because this is when the universal star formation rates and the AGN activity peak. The survey is ongoing. We select closely projected quasar pairs from Sloan and other surveys. The sideline to the background quasar probes the foreground quasar's host CGM. To date, in QBQ, we've confirmed 700 pairs to within 1 megaparsec separation. Shown here is a Sloan image of an example quasar pair J0853. The foreground quasar is at redshift 2.4, the background quasar is at redshift 2.5, and the projected separation is 112 kiloparsecs. 9 papers have resulted from the QBQ survey. I'm presenting the 8th and the 9th paper here. QBQ 8 is a statistical sample of quasar pairs observed with echelon or SGR instruments. We limit the pair separations to be less than 300 kiloparsecs. This is the loosely defined CGM boundary. Shown here is the example quasar pair again, J0853. In the background spectrum, you can see strong Lyman alpha absorption and metals coincident with the foreground quasar's redshift. This sample has 14 pairs. I searched for associated metals within 1500 kilometers per second of Z foreground. Column density profiles. On the left is a scatter plot of H1 column densities against projected pair separation. You can see a decline in H1 column with the impact parameter. And you can see strong H1 exists even beyond the estimated virial radius at 160 kiloparsecs. For comparison, I also show the literature work of the CGM of redshift 2 to 3 normal star-forming galaxies. They are typically less massive than quasar host galaxies. So the H1 columns of my sample are much higher than those of the coeval galaxies. On the right, we consider the carbon-2 ion. You can see absorptions within 200 kiloparsecs are strong and saturated. So we detect cool and enriched gas transfers to the quasar to at least 200 kiloparsecs. But I would argue it's unlikely that the quasar alone could transport all of this material from the ISM to where they are now. Because from the velocity spans of the absorption systems, I know the material has been accelerated to at most 500 kilometers per second. Then, even if a quasar has been on for 10 to the 8 years, the gas will still only reach 50 kiloparsecs. I generated cloudy photoionization models for each absorption system, and then I calculated the average ionization parameter U for each absorption system. You can see the ionization parameter U positively correlates with the impact parameter. And that means the quasar cannot dominate the ionizing flux received by the transverse CGM absorbers unless you have a really steep density profile. I applied ionization correction to the metal ions and the H1 column densities, and I found the median metallicity is minus 0.6 dex within 200 kiloparsecs. And I found nearly all the measurements show a supersolar oxygen to ion ratio. Baryon budget. With ionization correction, I calculated the total H column for each absorption system. I found the total H column does not vary with impact parameters significantly up to 200 kiloparsecs. And the median is 10 to the 20.5 per cm squared. Using the median total H column and the median metallicity, I can construct cumulative mass profiles of hydrogen and metals in the cool CGM, and it's plotted here. I estimated the total mass of the cool CGM is 1.9 times 10 to the 11 solar masses within the virial radius. And I estimated the infall time, and from that, I found the corresponding inflow rate exceeds 100 solar masses per year. So it's unlikely that quasars can quench the star formation at redshift 2. For comparison, in this plot, I also include the expected baryonic mass profiles following the NFW profile. So you can see that cool CGM accounts for only 1/3 of the total expected baryonic mass. So I suspect there is a hidden hot gas phase which is needed to complete the baryonic mass budget. I found several peculiarities about the quasar host CGM. One is evidence for elevated density. I'm showing the J1420 quasar pair here. I want your attention on the circled subsystem. The optical depth ratio of the carbon-2 excited state to ground state is 1.1. That requires an electron density of 160 per cm cubed, and the corresponding absorption path length is less than 1 parsec. For such small clouds, there has to be a large population of them to explain intersecting even one of them in my sightlines. Such small clouds are representative of dense knots in giant molecular clouds, but I checked the Lyman-Werner bands are absent. And I went back to QPQ4 to check the 2D spectrum of the pair. The color stretch here is residual flux after the quasars have been subtracted. And you see there is Lyman alpha emission at the location of the background quasar. This pair also has ALMA data, and CO emission is detected at the location of the foreground quasar. Farina et al. Is writing that up. Okay, move on to QPQ9. The motivation is a limitation of standard absorption line analysis of transverse sight lines. Regarding galactic scale flows, there is an inherent symmetry of the experiment. Positive or negative velocities may both be interpreted as flows to or away from the galaxy. But in a QPQ experiment, the radiation from the quasar may break the symmetry in the velocity field of the CGM absorbers. The goal is to characterize the dynamics of the gas. For this, I would need uncertainties in Z foreground to be less than the peculiar motions of the gas, and that translates to a precision of 300 kilometers per second or better. Here I present a stack of 32 spectra for carbon-2 analysis. You can see the absorption spans a large width and is skewed to positive velocities. I measured the centroid to be 208 kilometers per second. The intrinsic dispersion of the stack is 261 kilometers per second, taking into account of the broadening by redshift uncertainty. The centroid suggests an asymmetry that contradicts standard expectation, and the dispersion suggests quite extreme motions that greatly exceed the gas of any other galaxy populations. But note that quasar clustering implies a large dark matter halo mass, which implies a large line-of-sight velocity dispersion that is comparable to the dispersion measured in the stack. So outflows are not necessary to explain the large velocity fields. I offer two possible explanations for the asymmetric absorption. One possibility is an asymmetric radiation field that preferentially ionizes the gas at smaller Hubble velocities than the quasar. The cartoon here is a quasar that is blocked in the direction pointing away from the observer. So the gas observed in absorption preferentially lies behind the quasar. Another possible explanation arises from the finite lifetime of the quasar. The cartoon here shows you a light travel time argument. The light from the background quasar will travel smaller distances to reach the gas behind the foreground quasar than the gas in front of it. So the light from the background quasar may arrive at the gas behind the foreground quasar before the ionizing radiation arrives. Both explanations to the asymmetry would require the gas to be not in inflow, otherwise the velocity centroid of the absorption would be negative. Future directions. I am interested in integral field imaging of the CGM. I want to answer the question how often CGM absorbers are expected to be illuminated. And I pose a challenge for theorists to reproduce the observed quasar host CGM properties. So I note that Fauché, Jigeri et al. 2016 represent the only simulations that could reproduce the amount of optically thick gas observed, but they do not produce the extreme kinematics. My immediate plan is to study the line-of-sight CGM, which manifest themselves as narrow associated absorption line systems that can help me identify quasar feedback. Now, with all the tools built for absorption line analysis and also the databases for quasar spectra are built, there could be a lot other quasar absorption line studies for other science goals. These are all ideas for collaboration. Please come talk to me and maybe consider giving me a job.
All right, questions? So, can you go back to the, I was just trying to work out the light travel argument. So the argument is that the quasar turned on as the light was propagating from the background sources to the foreground sources? Is that?
Yes.
Okay. And that, what lifetime would that require?
I think it's very hard to quantify. Like, you can't really predict the quasar travel light time from here, but you can estimate it's reasonable because the extent of the CGM boundary is 300 kiloparsecs, and that corresponds to a light travel time of 10 to the 6 years. So that's within existing constraint of quasar lifetime. But it's a toy model. You can't really predict quasar lifetime from here.
Sure, I was just wondering what the constraints you need. Another question? All right, let's thank Marie one more time.